Okay, we're ready to begin. Oh, thank you. Okay, so then it's my pleasure to announce the first speaker, plenary speaker for today. And this is Patrick Ballard from Institut d'Alembert. And he's going to talk about transition from continuous to jumping solutions and quasi-static elastic contact problems with Coulomb friction, the prediction of the onset of break squeal. Please.
Thank you very much.
Patience.
So, good morning, everybody. That's a great honor to give the opening talk of the conference. I would like to thank the organizers first for inviting me, of course, and also for giving me a long enough slot to be able to share our recent findings with you. So this is joint work with Flaviana Iorlano. This is like this, okay. Flaviana Iorlano is from the Department of Mathematics at the University of Genova in Italy. But she was formerly in the Laboratoire Jacques-Louis Lyons at Sorbonne University. So I have a rather long title here. I'm going to explain it a little bit. Break squeal here should be understood as a generic word to mean friction-induced vibrations. So vibration can look contradictory at first sight with the word quasi-static here. It would, if the objective was to describe the vibrations, such as their frequencies, for example, but that's not going our objective here. It's common experience that in some cases, brakes can squeal, and in some cases, they remain silent. And we are concerned to make that prediction, and we will see that the quasi-static equations have the robustness to make that prediction. And we will also see that the good old Coulomb law of dry friction is also able to account for this phenomenon, which has been a centuries-long controversy. So let's start with the framework. All this talk will be concerned with the evolution problem raised by the quasi-static motion of a linearly elastic body above some fixed rigid obstacle and with Coulomb friction at the interface. So this is the evolution problem, which was first considered by Duvaux and Lyons in 1969. So I briefly recalled the formulation, which should be familiar to most of you. So this is a mathematical problem. So on one hand, I will have data, and on the other hand, I will have unknown. My convention will be to use the color red for all the data and the color blue for all the unknowns. So among the unknowns, I have the displacement field U, the stress sigma, which is a linear function of the displacement in the framework of linearized elasticity, and the traction T on the boundary. Oh yeah, and I will use the letter S for time. You'll have to get used to it, but T was no longer available. T was used for traction here, for tangential here. So time will be S. Among the data, I have the body forces, which may vary with time, the prescribed surface traction on gamma T, part of the boundary, and I have my contact conditions with friction on gamma C. So I recall them briefly. The first condition here expressed that the body is not allowed to penetrate into the obstacle. G is the gap between the initial configuration and the obstacle. So it basically encodes the shape of the obstacle. This is a function of space only. The obstacle is only able to repel the elastic body, and the repel force must vanish outside the contact zone, which is an unknown of the problem. Those Signorini contact conditions are classically equivalent to these weak formulations, and I will make essentially use of the third one. This is complemented by the Coulomb law of dry friction, the one that we learn at school, which is recalled here. So in red, I have F, which is my given friction coefficient. Vectors on the boundary are split into tangential part, index T, and normal part, index N, and the dot denotes the velocity as usual. So this is an empirical law proposed by Coulomb at the end of the 18th century on the basis of the experimental analysis of the motion of plates under the action of various forces. And this is equivalent to this more synthetic weak formulation, which is the one I will use in the sequel. So that's an idealization, but it carries all the feature of the phenomenon of friction and makes use of only one material parameter. So we are going to be concerned with the mathematical analysis of this evolution problem. Following Duvaux and Lyons, we will introduce a time discretization with time increment delta S, form a solution in red U I minus 1, and new solution unknown in blue UI. As the time increment is positive, I can multiply the last inequality by delta S and incorporate the time increment into the test function V here so that it disappears. I will drop the superscript and use W for the known former solution. So I have an incremental problem to study, which should be thought of as a step to study the quasi-static problem. As you can see, the incremental problem depends on the former solution here, but not on the amplitude of the time increment. This property is known as rate independence. This was introduced by, or at least popularized by Alexander Milke in Berlin. This is a very restrictive framework. It excludes all the dynamic effects and all the viscous effects. This is an idealization. It is very common in solid mechanics, as I will recall briefly. Some example of rate-independent processes in solid mechanics. You have perfect elastoplasticity. So rate independence means that you don't have any internal time scale in the system, actually. So you have perfect elastoplasticity, you have brittle fracture, we've just seen that you have contact with dry friction. We could also cite damage or solid-solid phase transition. All these problems have an incremental version and a time-continuous version. So in elastoplasticity, you have an evolution problem for the stress field and an evolution problem for the displaced field, for the displacement field. The corresponding incremental problems are minimum problems, and even convex minimum problems. In the case of brittle fracture, as formulated by Francfort and Marigot, the incremental problem is also a minimum problem, but it's no longer a convex minimum problem. Minimum problems come with a set of tools to perform the mathematical analysis. The reason why contact with dry friction is less understood up to now from the mathematical point of view than the other one is that the incremental problem associated with contact with dry friction is not a minimum problem. We shall see later on this talk what is its mathematical structure. A natural framework for studying those rate-independent processes is that of functions of time with bounded variation. They are characterized by the fact that their distributional derivative is a random measure. And they can have discontinuities of the first kind with a left limit and a right limit at each instant. So in rate-independent processes, we should expect discontinuities. And indeed, in brittle fracture, it's very well known that some infinitesimal increase of the load is able to yield a finite advance of the crack. Mathematically, it is connected to the fact that the quasi-static evolution problem will have spontaneous jumps in time. Mechanicians say that this is unstable crack propagation, and besides, when you try to apply a slow loading history on a piece of glass until it breaks, you won't be able to make it silently. You will have some noise, and this is connected to those spontaneous jumps. The picture is different in plasticity. So in plasticity, the stress field is governed by the so-called Moreau sweeping process. So what is a Moreau sweeping process? Think of a coin which lay on the table, and on top of that coin, put an inverted ball and start to move the ball slowly. When the coin is interior to the ball, it won't move. But when the boundary of the ball reaches the coin starts to move just as if pushed by the boundary of the ball. So this is Moreau sweeping process associated with a moving convex set, the ball here, C of S. Now, and one property, so it's naturally formulated in the framework of BV function. But if the ball moves absolutely continuously in time, then so will the coin. So the coin don't have spontaneous jumps in that case. Now, if C of S is, this does not work, oh yeah. C of S is the set of statically and plastically admissible stress field, then the corresponding Moreau sweeping processes is the rate-independent process that governs the stress field in elastoplasticity. And it has the property that every absolutely continuous loads induce absolutely continuous solutions. And the same is true for the displacement field. This was a theorem proved by Dalmaso. There is no spontaneous jumps in time in plasticity. Plasticity is a silent phenomenon. And besides, if you bend plastically a metallic spoon, you won't be able to hear any noise. So there is a difference of nature between elastoplasticity and fracture. However, you have, in perfect elastoplasticity, you have spontaneous jumps in space. The incremental problem for the displacement field is naturally formulated in a BV-type function space, which allow for spontaneous jumps in space, which are the shear bands in perfect elastoplasticity. In this talk, we shall see that contact with dry friction is hybrid. For small friction coefficient, it behaves exactly as plasticity. Absolutely continuous load will be proved to yield only absolutely continuous solution. So you have a silent regime for small friction coefficients. For large friction coefficients, I will show you that we should expect, and I will provide an example of that, we should expect spontaneous jumps in time of the solution. Despite absolutely continuous load, we have a noisy regime. The transition between the two regimes, the black slash here, is the onset of brake squeal. There is a transition of the qualitative behavior of the system for a critical friction, a critical value of the friction coefficient, and the analysis will provide a rigorous formula for this black slash. I will unveil it on slide number 9. Be patient. When we were working on the quasi-static equations for a continuum with Flaviana, we discovered that spontaneous jumps in time should be expected for large friction coefficients. So we felt the need to have a striking example in a simple system. So now I'm going to present that example, hopefully striking. I remembered this old paper from Anders Claubring, going back to 1990, analyzing the simplest finite element system that can arise by finite element discretization of the Duvaux and Lyons problem of slide number 2. So it has 2 degrees of freedom. It amounts to considering a particle with 2 degrees of freedom, evolving in an elastic quadratic potential characterized by this positive definite symmetric stiffness matrix under the action of a force varying with time with an obstacle here and Coulomb friction. So the equation here, equilibrium, contact condition, friction. And what Claubring did with this simple system is to analyze the rate problem. So the rate problem is the following problem. You're given a configuration, ut, so u is the displacement of the particle, t the reaction force exerted by the obstacle. There are vectors in R2, and you're given a rate of force. F dot is in R2, it's given, and you seek the velocity of the system as a vector over R2. What Claubring found out at that time was that for large friction coefficient, and he was able to derive the optimal condition in terms of the entries of the stiffness matrix, for large friction coefficient, you can have either multiple solutions for the rate problem, or, more disturbing, no solution at all. Then we thought, hey, here is our example of spontaneous jump. So, to write down properly the example, we have to have a notion of solution which allows for jumps. We have to have a BV formulation of the evolution problem. So let's put BV. And now we have to give a sense to each line of the problem. So this is equilibrium, must be fulfilled at each instant. No problem with BV function, which are functions. So this should be satisfied for all S. Remember, S is time for me. This should be satisfied at each instant, no problem. No problem with this one. But here, I must be careful. U is now a BV function. Its derivative is a radon measure. No problem to define the absolute value of a radon measure. And no problem to multiply a radon measure with a BV function, because BV functions are integrable with respect to any measure. But in case of a jump, typically, the derivative will have a Dirac mass at the instant of the jump. And you want to multiply here a Dirac mass with a function having a jump exactly at the same instant. So you have to be careful. You have to say if you are going to take the right limit or the left limit, you won't get the same evolution problem if you make one choice or the other. It turns out that the only possible choice is to take the right limit. Otherwise, it's very easy to have examples with no solutions at all. And there is a deeper reason, which is that, as we will see later on, there is an underlying sweeping process here. And the theory of sweeping process, as made by Moreau, found out that the natural framework for BV processes is that of right continuous functions with bounded variation. So here is our BV formulation of the quasi-static problem. It seems that it has never appeared, as incredible as it may seem. And we can now use it to show you that example of a spontaneous jump in time of a solution. So I consider here a large friction coefficient violating Clauberring's condition. And I will consider a loading history here, which is made of two affine functions of time pieced together continuously at time s equal 1. So in the first phase, I will apply a growing force F here, amplitude growing proportionally with time and fixed direction. And the force is designed so that immobility is a possible motion of the particle. It does not move. U stay equal to 0, and T is opposite to the force, and the force has been designed to be compatible with the contact conditions and this part of Coulomb friction. The aim of this first phase is to bring the system into a configuration where Clauberring found that there was no solution to the rate problem. And now I use the second phase of the motion to snarkily inject the rate of force for which Clauberring found out that there was no solution to the rate problem. And I found that the particle jumps into the air. Its position for time being between 1 and 2 is given by this, and it's a flying motion of the particle, which is at positive altitude at instant s equal 1. So I have a discontinuity in time of the motion. So this is an example of spontaneous jump. And you will ask, okay, but is it unavoidable? Do I have to jump? The answer is yes. If you take as initial condition the configuration just before s equal 1 here, and you apply this only the second phase of the load history, you can prove that there is no continuous in time solution. So this is an example of unavoidable spontaneous jump of the particle. So I know what you think. You think, how come that nobody in the computational contact community has ever pointed this out? That's because you don't have uniqueness in here. You can jump, actually, at any time between 0 and 1. So in the case of a time discretization, you can have a fast variation on a time interval of your time discretization. And then you consider a refined time discretization, and you will have possibly the fast variation at another place. Okay? So you won't be able to track, because of non-uniqueness, you won't be able to track numerically this jump. But it must exist nonetheless. We claim that this jump is what has been called informally by the community for decades as a frictional instability. Okay? So now we have an example of that. And in the case of the two of Clauber's system, we have an optimal condition for which those frictional instability can show up. So what we have done is to extend that analysis to the case of a continuum, yielding the counterpart of Clauber's condition to the case of a continuum. Slide number 9, remember. So here is a compendium of results for the mathematical analysis of Clauber's simple system. So you have, for Clauber's system, you have an incremental problem and a continuous time problem, as for the problem of Duvaux and Lyons in slide 2 for a continuum. So the results for the incremental problem have been known since the 90s. So the incremental problem is always solvable for arbitrarily large friction coefficients. When Clauber's condition is satisfied, the solution is unique. But when Clauber's condition is violated, you can always find example of force for which you have multiple solutions of the incremental problem. Now, these results, I believe, are new for the quasi-static problem. So we are given an absolutely continuous force here, F. Then you always have a solution, but you must make the analysis in BV because of the spontaneous jumps. If you don't take BV, you won't have always a solution, even for loading history being C infinity, for example. What we have proved is that under Clauber's condition, all the solutions are also absolutely continuous. So they don't have any spontaneous jump. But whenever Clauber's condition is violated, then you have examples of smooth loading history with no continuous solution. So you can't avoid spontaneous jumps in the solution. So I believe it was in the mind of the community that Clauber's condition was somehow related to a condition for friction instability. And by analogy with Euler buckling and loss of uniqueness of equilibria in Euler buckling, everybody thought that the condition of uniqueness of solution for the incremental problem was the condition for those friction instability, and that would be the one which would be able to give the counterpart of Clauber's condition in the case of a continuum. But no one was able to find a uniqueness result in case of the continuum incremental problem with small friction coefficient, or example of multiple solution with arbitrarily small friction coefficients, including me, because I tried to do that, but I never succeeded. What we have discovered is that the right point of view is the point of view of considering the possibility of spontaneous jumps in the quasi-static problem. And because we considered that, we were able to find the counterpart of Clauber's condition in the case of a continuum, or in the case of an arbitrary finite element discretization with an arbitrary number of degrees of freedom. So what we have done, and I'm going to present briefly the result we obtained for a continuum, was first to generalize the theorem of existence of solutions for the incremental problem and arbitrarily large friction coefficients. That's because we unveiled the underlying mathematical structure, and this is the first result that has ever appeared for large friction coefficients in the case of a continuum. What we have also proved is to identify the counterpart of Claubrink's condition for a continuum, slide number 9, and to prove that under this condition, the quasi-static problem is always solvable. So let me try to show you the mathematical structure of the incremental problem and that of the quasi-static problem for a continuum. So unfortunately, it's going to be a little bit more technical, but this will be short. So here are my equations for the incremental problem for a continuum. These equations are exactly the same as the one that appeared on slide number 2. I have just swapped the order of friction here and unilateral contact here on gamma C. And I have used a weak formulation of the contact condition on gamma C. Okay, so let's start to work on this set of equations. As is usual for this kind of problem, the Dirichlet condition here, the clumping condition, is put into the space in which we seek for the solution. So the Dirichlet condition does no longer appear in the equations of the problem. Now I'm going to gather the 3 conditions here, this one, and this one, into one weak variational inequality, which is equivalent to that 3 conditions. So basically, what I have done here is to put the problem under the form of 2 coupled variational inequalities. Okay? Now, I make an essential remark, which is when Tn is given, Tn is not given, it's in blue, remember. It's one of my unknowns. But if, as a first step, I suppose it is given, then this inequality is the optimality condition of a minimum problem. And a very simple minimum problem because it's a strictly convex coercive minimum problem having a unique minimizer, provided Tn is given. So the unique minimizer will fulfill all the equations of the problem, except maybe the contact condition. The minimizer possibly can penetrate into the obstacle. But I have to adjust my Tn here so that it does not do so. And that's what I'm going to do using the solution operator of this minimum problem and formulate the contact condition in terms of a variational inequality involving the solution operator of that minimum problem. So now I have put the incremental problem for the continuum as a variational inequality involving a nonlinear operator that encodes elasticity and friction. And so what's the interest of doing that? The interest is that I can rely on an old contribution by Chaim Brezis, who tried to identify the most general class of nonlinear operator for which the variational inequality can be solved. He called this class of operators pseudo-monotone. So a variational inequality associated with a coercive pseudo-monotone operator is always solvable. So here, it's very easy to see that R is always coercive in arbitrary dimension. So the problem, to solve the incremental problem, is just to prove that R is pseudo-monotone. And this is difficult. We proved that it is a Lorentz operator. This is a subclass of pseudo-monotone operator. And to do that, we have to prove a specific compensated compactness result. We proved it in 2D. We are currently doing this in 3D, but this is very difficult. But we believe that we're going to succeed to do that in the end, so that we had an existence result for the incremental problem and arbitrarily large friction coefficient. I said isotropic here because in the case of anisotropy, it can break. And we have an example of non-existence of solution for the incremental problem in certain cases of anisotropy and large friction coefficient, but we obtained the optimal condition for that. Okay, so let's turn to the quasi-static problem for the continuum. I will rely on the solvability of the incremental problem to get an existence result for the quasi-static problem. So the quasi-static problem, these are the equations of slide 2, those of Duvaux and Lyons. And just order of this swapped, friction first and contact condition second, under weak form. I put the Dirichlet condition on the space, and I bring together the first three conditions, exactly as for the incremental problem. And I get two coupled variational inequalities. But now, in the first one, I have the velocity. So it's no longer the optimality condition of the minimum problem, but if Tn is given, this variational inequality is actually a Morrow sweeping process in H1. So it is naturally formulated, thanks to Morrow, in BV. So I have a formulation of the quasi-static problem, which accounts for the possible occurrence of spontaneous jumps in time of the solution. So we use the solvability of the incremental problem and try to go to the limit, time increment going to 0, to prove that one can solve the quasi-static problem for a continuum. We found out that to preserve the property of sweeping process to yield absolutely continuous solution for absolutely continuous loading history, we had to require a condition on the friction coefficient, and we were able to find the optimal condition. This is, we called it condition C. This is the counterpart of Claubrink's condition in the case of a continuum. And we arrive at slide number 9. So I'm going to show it to you. So this is a condition which link the friction coefficient, the elastic moduli, and the geometry only. So omega, gamma u, gamma c, and gamma t. This is a supremum which must be smaller than 1. It reduces to Claubrink's condition in the case of Claubrink's system. And it can be proved that in the case of a spatially homogeneous friction coefficient, because in that condition, F must oscillate with space, for example, but in case of a spatially homogeneous friction coefficient, this condition reduces to a range for the friction coefficient, a non-empty range with a positive critical value of the friction coefficient, depending only on the geometry and the elastic moduli. And under that condition, we prove that there is in case of 2D isotropic elasticity, there is a solution for the quasi-static problem. For any BV loading history, there is a BV solution, but whenever the loading history is absolutely continuous, the solution is also absolutely continuous. So under that condition, the solution cannot have any spontaneous jump in time. So this condition is the condition, is a counterpart of that of Claude-Bring in the case of a continuum. It's a condition which says if the friction coefficient satisfies that condition, is small enough, whatever is the loading history that you consider, you won't have any jump. You won't, there will be no onset of vibration in the system. This is uniform condition C because when it is violated, you can have spontaneous jumps from some load history and some other do not have spontaneous jump. And we are able to derive also a weaker condition C specialized for a given loading history. This one applies to any load history that you can imagine and is the condition preventing the appearance of spontaneous jumps. Last slide, references. So the first paper is the paper who gave the first existence result for the incremental problem with arbitrary large friction coefficient. The second paper is the paper deriving condition C and proving the existence of solutions for the quasi-static problem under condition C. So it was submitted to a top-tier journal of mathematics. This kind of journals, they send very few papers to review, but when they do, it takes a very long time. The peer review process takes a very long time. So it's been reviewed for 9 months now, but it's available on Archive. In this one, we have written down with Flaviana the existence result of BV solution for the quasi-static problem and arbitrarily large friction coefficient in the case of Claude-Bring system. And we are currently extending this to the case of a continuum. It is necessary for that to enter deeply in the structure of the spontaneous jumps. This structure is simple in the case of Claude-Bring system, more involved in the case of a continuum. These papers have been written for the mathematical community, which requires a rigorous proof for any tiny details. So it involves many technicalities. But if anybody is interested, I will answer any question by email to translate to the contact computational community. Just one word to conclude. The structure that we found out in the case of the incremental problem strongly suggests a numerical approach. Because it is a minimum problem coupled by with a variational inequality. So you guys have solvers to solve minimum problems, convex minimum problems, and solvers for variational inequalities. So I don't do numerics. But if I were, I would try to stick to this mathematical structure, which is the only one that was able to yield existence of solution in the case of arbitrarily large friction coefficients. Sorry if I was too long.
Thank you very much. I'm sure we have questions. Please.
Thank you for a nice talk. I would like to ask, could you relate to any kind of regularization? Because I noticed that when you introduce this bounded variation space and time, at the same time you are assuming that your fraction is not h minus 1 half, but it's
There is no regularization, so the analysis is for the sharp equation without no regularization at all. Actually, but we have a little bit of regularity of Tn, which is your concern, because of the contact condition. As Tn is non-positive, it is a measure. So it's not only in h minus 1/2, it's also a measure. So it provides a little bit of regularity, but it's not much. But it's essential for the analysis of the incremental problem.
Thank you. Second row, first row, and then we go there. Please, yes.
Thank you very much. I'm wondering, there's a question of scale. If we talk about regularization, if we zoom close enough to the interface, we will see a transition from sticking to slip, a crack material.
Yeah.
Before it's formed. Or for example, we say plasticity is silent. My hearing is not good, but if you have very, very good ears, you could hear it. And in fact, it's probably you can hear the jerky motion of this location.
Probably, but on the macroscopic scale, you don't hear much noise, and I connect that realistically to the fact that you don't have spontaneous jumps in time, so no excitation of vibrations at a macroscopic scale.
So to continue along this track, I tend to want to regularize things. To model stick slip, for instance, I will put a slip weakening cohesive. But what you're telling me, what your message is that this is not necessary.
Yeah. And actually, if your aim is to find the critical value of the friction coefficient, you should not do that, because you will need to analyze in the end the dependence of the transition, the critical friction coefficient, on the regularization that you introduced. And this will be more complicated than working from the beginning, from the start, with the idealized problem.
Now, imagine I would like to test experimentally the cloud-ring problem.
Yeah.
What kind of motion would I expect at the jump? Is it a particle that would go out of contact with the plane, for example? Or,
yeah.
Or is it
Okay. That will be, for me, the occasion to comment a little bit more on this. So, yeah, if you try to make the experiment, you will have a jump into the air. So, what happens with the dynamic equations, which is necessarily the one which will describe your experiment? So it's interesting because in the case of the dynamic equation, so now I have a mass and an acceleration, there is a unique solution for this. I proved that in another paper. For any initial condition and any loading history here. And what happens is that the only dynamic solution will remain at 0 in the first phase of the motion. Okay? And in the second phase of the motion, the dynamic solution will not jump. It will be continuous in time, but it will start to raise very, very quickly into the air. And the lower will be the mass, the faster will be the flying of the particle. And in the limit m going to 0, you will have a discontinuity of the motion, a discontinuity in time of the configuration. So this is also connected to your questions. It's better to work actually with a quasi-static equation, putting apart that the fact that they are simpler on the mathematical point of view than the dynamical equation. But the dynamical equation, you have a solution. Well, okay, but it's hard to see the qualitative property of this solution. Here, working with the quasi-static equations instead of the dynamic equations, you can track jumps. And jumps or some trace of very rapid variation of the dynamic solution, excitations of vibrations.
So if you are in real life, I would say, so you don't have a point-like contacts, you have some elasticity at the interface, maybe some viscosity. Do you expect those aspects to regularize the problem and avoid the jump? Or
No. We have also, and it's in the paper, we have also built an example of spontaneous jump in time for the quasi-static problem for a continuum. So it does exist too for a continuum. So no regularization. These jumps or the excitation of vibrations, it's the same story as for brittle fracture here. Brittle fracture is noisy, basically, because you have spontaneous jumps of the crack because of unstable crack propagation. And it generates noise. And some people say, well, that makes brittle fracture inherently a dynamic process, which should only be analyzed in the framework of elastodynamics. But the theory is not available yet. The elastodynamic brittle fracture theory is not available yet.
Could you show one of the last slides where you had the Carbon's condition and your condition?
This one?
No. No.
Next?
No. Next.
Next?
Next. Next.
Oh, yeah. Number 9. This one.
Right. Something's must be okay. Okay, you take the soup over U and V.
Yeah, yeah.
U is not the solution.
No, it's not the solution. This is a supremum. Yeah, yeah. I should comment on that because.
One more question. The right-hand side, you have conditions of the data on the stiffness matrix and the loading, and I don't see any on the left-hand side. There's nothing on the say constitutive law or.
Oh yeah, you have, but it's a little bit hidden. It's there. Here you have elasticity, and the rest is geometry, actually. So you have friction, elasticity, and geometry only in that condition. So it's the raw condition that show up in the mathematical analysis. So it's not designed to be easy to compute, but it is what it is. I hope that somebody will be interested to try to explore that numerically. It's probably difficult to compute, but it would be very interested in real problems to have an approximation of this critical value of the friction coefficient, just to know if vibrations are to be expected or not, if your brake is going to squeal or not.
This is the most horrible thing is that you have fractional logs and negative logs, but they are so to say mathematically correct ones. So
no.
Then you have the sigma u minus v dot n in L2. So
no, this is not going to be a problem because you will consider a finite element discretization of your body, so you will be able to handle that properly. Sorry?
You are not speaking about finite elements at all. I'm just saying that a little bit to the right now. So the sigma u minus v dot n in L2 is for a pure mathematician.
Oh yeah.
It's the wrong concept.
Well, it's what. Well, I'm sorry. It's what shows up. But that should be possible to compute. Of course, computing this, precise computation of the critical value will be very heavy numerically. I'm well aware of that. Well, that's what it is. I don't know what to say. But it would be very interesting to have methods to compute that and to get good approximations to good assessment of what critical value of F behave, how it behave with elastic moduli, for example, with geometry. Do I have to have a slender body or a round body to have the largest possible critical F here? I don't know. It remains to be explored. But that's the rigorous condition arising from the mathematical analysis. And this is exactly the counterpart of Claubring. It says nothing. It says only about the spontaneous, the appearance of spontaneous jumps. It's only about that. It's not about uniqueness for the incremental problem. I know nothing about that for small friction coefficient.
So we have at least two additional questions. So, I have a question on your modeling choice when you define the quasi-static problem in the setting from your slide 5. So you told us that if you choose the left limit, it doesn't work.
Yeah.
So you have to choose the right limit.
Yeah.
And I have a question about the dissipative property of this friction law. You know, when you start right friction law, if you have discontinuities, and if you want to compute the dissipative power, most of the time you are in trouble with if you choose only the right limit. And what about choosing the average between the left and right limit?
No, it doesn't work. It's the same. You have an underlying sweeping process here. In the case of a sweeping process, with the ball jumping from location to location, you have to take the right limit. Otherwise, you're not able to solve it.
I don't agree with that because you need to have the right limit in your condition of friction law, but you can also use the average between the left and the right limit.
Yeah.
And if you do that, if you know the work of Michel, then you get a friction law that is dissipative. Otherwise, it is not.
It is.
In that case?
It is dissipative, yeah. Yeah.
So then, next question.
I'm still struggling with the main message. So I understand that you can predict the jump, the onset of discontinuity. But the path to get there, is it important from a physics point of view? Does it matter if you want to figure out if you have a violent earthquake or something less destructive? Does it matter the details of this jump and the dynamics fact of this jump to assess the energy that is radiated out of your system?
Yeah, it reminds me what Claubring has written in this paper. Claubring says informally that the reason why I may have non-existence of solution here, there is only a sentence in this paper, is probably there must be some kind of jump so that the quasi-static equations are no longer available. He says that, so I don't want to study that. So that's what he says, and this is reasonable. This is exactly the same thing as people saying that brittle fracture should not be studied in the framework of quasi-static elasticity because it's inherently a dynamic process. The same can be said, I agree, for contact with dry friction, but only in the noisy regime. In the silent regime, the quasi-static theory is perfectly valid. But the analysis of spontaneous jumps enables to find the validity domain of the quasi-static analysis, actually. You should think of this like that. Okay.
Going back to slide 9, because you have this set of solutions, right, which is your A of something.
Slide 9, here we are.
It is A of F. Is there anything known about the structure of this set?
It's convex. No, is it convex? No, I don't know. I can't answer. We did not investigate that.
So that's just the solutions, how they occur.
Yeah, actually, the name A is because it's defined the admissible condition. It's admissible in the contact condition. So the value of Tt smaller than minus Ftn, so part of rho, and you have to fulfill the Dirichlet condition. You have to fulfill the equilibrium with the forces in some sense. So you have for each F of 0 and T of 0, you have an inadmissible set of initial conditions, and this is the union of all the admissible sets for all possible values of F and T.
Probably because you're investing a certain amount of regularity in the definition. This is why I was asking. Okay.
Yeah, the regularity is the regularity for which I am able to make sense to everything and to have a finite elastic energy.
If there are no additional questions, then I would like to thank our speaker very much. We are 2 minutes ahead of time, so we will happily continue.
Yes, it's on the stream.
Well, you're right, sir. We actually there from
So you can prepare